Greeting Earthlings, if you follow the channel, you know that we are hard at work restoring the Apollo communication hardware. Over the last year and a half, you might have followed our steady progress. In the last episode, we showed how we finally reached the point where we could exhibit a working setup at DesignCon. We had television, voice-up, and part of the data transmission working. You might recall that at the last minute I even managed to add the famous Apollo beeps, known as Quindar tones. The real one sounds like this.
Tranquility Base here. The Eagle has landed.
Roger, Tranquility. We copy you on the ground. You got a bunch of guys about to turn blue. We're breathing again. Thanks a lot.
And my version is like this. 13 at your convenience. Give a stir to your oxygen tanks. In this episode, I'll explain briefly what Quindar tones are. I also give some details on how I hacked a cheap commercial microphone setup to add Quindar tones. Quindar tones were added to transmissions in the Earth to spacecraft direction only. They were not present in the other direction. They consisted of an intro tone, a 250 millisecond burst at 2525 Hz. At the beginning of the upvoice transmission. It was automatically triggered when the Houston Capcom pushed his push-to-talk button. Then at the end of the transmission, as the Capcom released the button, an outro tone was emitted at a slightly lower frequency of 2475 Hz. These tones then traveled via telephone lines or other dedicated means to the actual transmission stations, which would generally be very far from Houston. Of the three major transmission deep space stations, one was at Goldstone, California, another one in Madrid, Spain, and a third one in Honeysuckle, Australia. They were widely and equally separated over the globe, so that one was always in view of the spacecraft as Earth was rotating. Once received at the ground transmit station, the Quindar tones were used to trigger the equipment. When the intro Quindar tone was detected, it turned on part of the voice transmission chain. The equipment was turned off after receiving the outro tone. There was no need for that on the spaceship side, since the transmission equipment was directly connected to the audio source. The upshot is that Quindar tones were originally meant to be used by machines only. However, in practice, they proved useful to the astronauts too. The tones cued them on the beginning and the end of the transmissions, and when it was their turn to speak. This was particularly helpful when there was over a second delay in the transmission of voice from the Earth to the Moon. The astronauts responded right away after hearing the outro beep, without waiting for the normal blank in the conversation. It made the delay much less of a hindrance. Tones were so useful that they were reinstated on the shuttle missions, even though the equipment did not need them anymore. So guys, this is something I wanted to do for a long time, is the Apollo Quindar tones. And the two tones you hear, the intro and the outro, they were automatically generated. So interestingly, they are only done on the ground. These are transmission controls. And they became so emblematic that they are just associated with space flight, and particularly the Apollo flight. It's a convenient way to know when the senders are finished talking. Apollo 11, this is Houston, over. And you know it's over, it's time to respond. So the astronauts used to key on that. They did not generate any of these tones. This is only for Earth transmission. And I did it with a little bit of old-fashioned electronics. I'll show you how. So my Quindar tone generator is definitely old school. You would be tempted to use only digital electronics for it, but there is a catch. The tones are pure sinusoids, which are not so simple to produce using digital electronics. So it turns out the Quindar tones are the simplest form of what's called FSK, frequency shift keying, where you use two different tones to transmit information. That's one of the first way of encoding digital information on an analog media, such as a modem or a radio. And if I turn it on, and you have two tones. And the reason I had one wired up is because this is used for radio teletype, and I was just doing a radio teletype transmitter. The decoder we don't use in this, so I'm just using this circuit and that circuit, and I'll show you what that is. So the bottom one is straight from the application sheet of the XR2206, which is an FSK generator, and it's basically the HP 3300 in an IC. It uses the exact same principle. It's a generator that you can use to do very good sine, square wave, or triangles. But on top of that, they added the possibility to choose from 2 different current sources, so you can switch between 2 frequencies really quick and in a phase continuous manner, which is important for FSK. And depending on the value of the logical input you have on the pin over here, you get either a low tone or a high tone, and it gets out. I use an oldie but goodie, the 74123, which is a dual mono stable multivibrator. And you can trigger them either going down or going up, and I have one that's wired for going down and one that's wired for going up, and I tuned them to give me both 250 millisecond pulse, and that's the circuit right there. I have my little button. You can tell the 2 sides have their timing resistor, timing capacitor, and adjusting resistor, and the 2 outputs come here. And then they go into those diodes, so that you could use an OR gate, but since I had only to use one gate, that would be wasteful. If either of the outputs is low, it will put the output low. If they are both high, the diodes are not conducting, and the resistor will put this level high. There's a little capacitor and resistor to smooth the transition, so I don't get a pop. So the frequency comes out over here, and here I have a little MOSFET on to suppress the signal, and turn off to make it go through. Circuit over there, and that's my little gate. So if I go to the continuous signal, warning's loud, and if I get it after the gate, I then hacked a cheap intercom system from Retekes. It had a nice weighted base with a gooseneck microphone and a mute button that was begging to be reused as a push-to-talk button for Quindar tones. After a bit of reverse engineering, I was able to access a few points on the panel daughter board, enough to steal the 12-volt power supply, connect the button contacts, and find a spot to inject my tones. I'll put a link to my lab book notes with all the gory details, should you want to try to do the same. Now came the time to try this ungainly prototype. Apollo 11, this is Houston, over. Okay, this seems to work convincingly. Now I just needed to shrinkify this. Note that for the final board I substituted a CMOS CB4096 in place of the TTL74123 circuit, so I could power everything from the 12-volt supply in the microphone base. I did not have the time to make a nice schematic or PCB, so I just wired everything up on a Perma Proto board from Adafruit, and in the Retekes box it went. So okay, it isn't quite perfectly close, but for a demo that's going to be good enough. 13 at your convenience, give a stir to your oxygen tanks. Okay, it sort of kind of works. Hello, this is Houston. But this one is such a better microphone, you can't even hear it. Apollo, this is Houston. It's so much clearer on the better microphone. This is the cheap microphone. So you can hear the difference even on the Apollo transmission system. Get good mics. And voila! An Apollo-themed microphone you can use on any occasion if you ever wanted to go on the air with a flare, or find yourself having to call someone on the moon. See you in the next episode!